Hello and very warm welcome to this very first lecture of this course, Probability Methods and Probability Methods for Civil Engineers. Basically, there are 7 modules, and this is the first module. And in this first module, we have one lecture on probability and its role in civil engineering. You can contact me for any queries through the email IDs that is shown here, or the other contact details which is shown on my homepage. In this course, we will take you through different methods, different probability methods, different tools that is very useful for different specializations in civil engineering. And in this first lecture, the motivation of this first lecture is just to tell you that how important is this particular these probability methods for almost for all the specializations in civil engineering. So this is the outline of today's lecture. First, we'll talk in general engineering, that is application of probability methods to the engineering in general. Then we'll give the starting of this probability concept. This concept will be discussed in detail in the subsequent lecture, but to start with, we'll just give where we start and what are the basic difference between the traditional techniques and the other the technique that is used in probability. Then we will particularly come to this civil engineering aspects. There are different facets of the civil engineering, starting from environmental engineering, geotechnical engineering, structural engineering, transportation engineering, and water resource engineering. There can be other specializations also. This need not be the all the specialization that can be think of, because the area of the civil engineering itself is very vast. So we'll just try to give you the glimpse of each and every all these specialization where the probability methods can be applied and its role, and we'll conclude with some remarks on this probability methods. Basically, this probability theory provides a formal basis to quantify the risk or uncertainty in engineering problems. To start with, this is the concept that just before, if we don't want to use this particular theory, then generally the judgment that is the first property of any engineering, including the civil engineering, that we generally apply our engineering judgment with some kind of the qualitative approach. But we have seen in different applications that the source of uncertainty is so high that we need some formal point, we need some formal approach to address this uncertainty, and here is the very important role that the probability methods play. Before we start, these are very important points that we should talk on, is that there are some true things and there are some false things that generally goes on. So basically, to start with, the probability theory is not the remedy for all engineering problems. I want to start with this because it should not be thought at the beginning that okay, the problem that cannot be addressed by this traditional techniques, the deterministic technique, I will address it through the probabilistic theory. That not necessarily be true for all the engineering problems. Where there is some randomness, where there is a source of uncertainty is there, that kind of problem, even though some qualitative solution or some engineering judgment or based on the experience of the field engineers is available, that thing also we can revisit those problems to take care those source of uncertainty through different probability methods. So all the engineering problems which are not solved by the traditional technique can be solved by probability theory. That is not true. On the other hand, sometimes we generally have a belief that a large number of data set is needed to apply the probabilistic method. That is also not necessarily true always. Which is true is that is that the proper representation of the probability, the proper representation of the population in my sample data set must be there. Otherwise, what happens is that if I take a particular area, if I take a particular zone, that particular area of the support, that all these things will be discussed in the later, particular area of the support, if I select to take my sample, that may lead to some wrong result. That is why generally we say that we need a very large data set. But the true thing is that if we can take a sample, start with a sample which is a proper representation of the population for the problem in hand, that is sufficient for the probabilistic analysis or probabilistic methods. And the last thing is the probabilistic method and the deterministic methods are not mutually exclusive. That means that if some problem is there and that cannot be solved by deterministically, so I can solve it by probabilistically, or vice versa, that is solved in probabilistically that cannot be solved deterministically, is not true. So there are some other methods also available which we can also adopt. That depends on the what is the type of problem, what is the nature of problem, and what is the most economic solution that you can get. So depending on all these things, you can select which solution is to be taken for a particular problem in hand. So that's why it says that the probabilistic and deterministic methods are not mutually exclusive. To start with the probability concept, it generally says that the probability is the quantification of occurrence of an event in a random experiment. If the outcome of one experiment is not certain, it can take any value, then the occurrence of a particular outcome can be expressed in terms of a probabilistic sense. We can start with the very common example of tossing a coin or throwing a dice, that the outcome of the tossing a coin can be head or tail, depending on means these are the two things that can happen. Before I come to this is generally expressed in terms of a number between 0 and 1, and obviously including these margins. That gives an idea is that how likely an event will occur. This likely is very important. That generally gives a concept of this expectation. For example, that I was talking is that if suppose that a fair coin is tossed once, the result will be either head or tail. So the probability of having the head or tail is 0.5. But or if I say that it is a throwing a dice, or the probability of coming that outcome of any particular number starting from 1 to 6 is, if it is fair, means all the outcomes are equally probable, then the probability is generally said to be 1/6. But if you do the experiment, if you take a coin and throw it for 10 times, it doesn't guarantee that you will get exactly 5 numbers of heads. You can do this experiment with you, and you can throw the coin for 10 times and count that how many times you get head, and it is surprisingly true that it is very rare that you will get exactly 5 heads out of 10 toss or out of 10 experiments. Then what does the 0.5 indicate? The 0.5 indicates that if you throw the coin for a large number of trials, for the infinite number of sequence of this trial, then the outcome of head generally on a long run is probable to have the 50% of the chance. So for any finite number of experiment, it doesn't indicate that exactly 50% of the times one particular outcome will come. That is not the true. So this is basically the concept of the frequency analysis, where the frequency of a particular outcome is expected is the frequency of a particular outcome on condition that the number of trials are infinite in number. That particular frequency is generally the starting point of the classical probability theory. Obviously, we'll discuss about this in details in the subsequent lectures. Coming to the civil engineering in particular, there are different specialization where generally the nature of problem that we have to handle is different. Starting with the alphabetical sequence, it starts with the environmental engineering, geotechnical engineering, structural engineering, transportation engineering, water resource engineering, and obviously, as I told earlier at the starting of this class, that this may not be mutually exclusive, that there may be some other fields also where the application of the probability methods is very successful and found to be very effective. In the operations, there are different situations where with this probability methods can be applied. For example, the system identification and the model selection. In a particular system, if we know that input and its corresponding response, then I can identify the system in terms of its parameters. The damage and deterioration, particularly in case of the structures, this can be useful, very much useful for the probability methods can be very useful. The loss estimation, particularly in the for example, that seepage loss through a canal, this loss estimation can be very useful for this probabilistic method. If we think of that risk assessment and management, which is very well grounded on these probability methods, where the theory or many tools or many methods of this probability is applied. Hazard analysis, probabilistic design of structures and other components of this civil engineering structures particularly. Then risk-based optimal design and the maintenance and inspection of any kind of civil engineering structure that you can think of. So these are the operations where I can use the probability method, different probability methods. So to start with the environmental engineering, the environmental risk assessment is one of the most important issue where we need the different probabilistic method. And for example, that here the issues are shown as the health effects of the community, the impact of natural resources or the man-made structure due to the pollution, and very recently we have seen that this change in climatic conditions. So if there is any change in climatic condition, how it is going to affect the particularly the water resource or the environmental problems in civil engineering. How can this probability, say for example, that if there is some change, we are not very sure about the outcome, particularly in the climatic conditions. So a probabilistic prediction, a kind of uncertainty quantification of the particular outcome, and depending on the change condition, that can be done through uncertainty quantification. Coming to that, there are different models can be used. The first is the parametric models. Either it can be through the different distributions of this probability, where we estimate the different probabilities based on the data available to us. If it doesn't fit to particular distribution, we can go for different types of non-parametric models, where we generally don't use any particular distribution, but we generally go for in a non-parametric way. In between this parametric and non-parametric, there could be some semi-parametric approach also. The part of the model can be non-parametric and the some other part or the estimation, particularly in the data analysis, can be parametric. So that kind of thing are known to be the semi-parametric models. There are obviously the empirical models are also there for this kind of problem. One thing I want to mention at this point is that even though these particular issues are mentioned under the umbrella of a particular specialization, for example, these things now what I am discussing is under this environmental engineering, but you know, these are all interrelated. It is not that this kind of thing are only for the environmental engineering. This can be as well be true for the geotechnical engineering or the water resource engineering or the structural engineering also. But in particular for this environmental risk assessment, if we see the operations, then we can go for the estimation of the input parameters. There are some input parameters are there. There are different methods are available. How can we estimate that input parameters? Identification of the probability distribution, again there are different methods. How can we identify which particular probability distribution can be best fit for the particular data that is available to you. All these things we will discuss in the subsequent lectures, how to do these things. Determination of the dependencies among the variables, if the variables are interrelated, if the variance depends on each other, then whether that kind of dependencies can be determined, which is also very important, particularly in that interrelated problems. The last is that estimation of the model uncertainties. This is very important in the sense that each and every model that we used for a particular problem, always this model, not a single model is perfect. So that due to this model, what are the different uncertainties is there, that also we can quantify, and that will be that with compared to the a particular information just on a particular number, if we give some kind of the some uncertainties also, and that model uncertainty in particular, that will be very useful to the end users. Coming to the geotechnical engineering, there are different sorts of uncertainties. For example, that variable nature of rock and soil properties and other in-situ conditions, reliability of the design and construction method, whether that particular design and the construction method that we are adopting, whatever the analysis, whatever the assumption was there while we do the analysis, whether that is having some effect for a particular method of the construction or construction that is being adopted in the field. So depending on the which field condition or which construction method we follow, that could be some kind of uncertainty may be related to this. Then the cost and the benefit of this proposed design strategy. The cost and benefit is generally that we generally always go for an optimized design, whether we generally always minimize the cost and maximize the benefit. So all these things, when we go, there are different source of uncertainty that is generally developed for different geotechnical aspects, and those things should be taken care of through this kind of probability models. Then if we see that uncertainty and probability assessment, this can be done through a very basic approach to start with. So for example, the histogram analysis, whatever the available data that is available to us, that we can use for our the very basic, and start with different statistic analysis, start with the histogram analysis, which gives generally some idea of the frequency over the different part of the range of this particular variable. We can go and we can go for the sample mean, variance, or the standard deviation. Standard deviation is nothing but the square root of the variance. Mean generally gives you the where the data is that there is particularly the first moment, the variance is your second moment, and square root of that is the standard deviation. These will give you the different. So these are only the first two moments. The third moment can be your skewness, fourth moment is kurtosis. So these things can give some idea of the data that is available to you. The coefficient of variance, similarly, that is a standard deviation by mean divided by mean, that will give you the coefficient of variance. So this variance, this particular coefficient, that is CV, that is coefficient of variance, that how the data is varying over keeping the mean as a center. So these things will give you that how variable is your data is. Then different probability density functions, PDF is the short form. Different probability distribution function can be used to represent your data, and there are many probability distribution. Either it can be continuous, it can be discrete, or this can be sometimes there is a mixed distributions are also available, particularly for this rainfall estimation, where there are many values can take 0. So at the 0 there will be an peak. So depending on that, on the nature of your data, you can select a particular type of the distribution, and you can represent your data in terms of that. Estimation of in situ properties from the soil sample. So different properties when you go for particular construction, and with the in situ properties of the soil samples, we generally estimate from the actual from the actual field condition. So that estimation is also can be done through different probabilistic method for the properties of the soil samples. Then comparison of the field test and the field performance data. So first we go for some testing, and then we go for to check their performance. So how they are, whether, so we can again estimate some kind of distribution of these two things, and we can compare how close, or if we say some particular attribute, say that whether there some particular parameter of the statistical parameter are same or not, or something is more than another one, then we can go for some kind of hypothesis testing to compare the field test and the field performance data. Coming to the structural analysis, generally in the structural analysis, where you know that this extremely low rate of failure is generally provided, and this is known as the low probability and high consequence risk facility. So in any structure against the failure, we generally allow very low probability. If because if that failure is occurs, the consequence is excessive in terms of monetary loss or injury or even death. So we generally provide very low probability for this kind of structural analysis. Then in the probability risk analysis, we can define the context and the system. First of all, we have to know that for which particular application we are going to adopt this one. Then we identify the hazard scenario, what are the different hazard that can come for a particular issue, for a particular aspect. Next, we can see that analysis of the consequence. So how important is that consequence? That is the most important thing. The estimation of the probability of the occurrence. So different failure mechanism or different failure types can occur. So we can estimate the probability of different occurrence. We then based on this, we can identify the risk scenarios. Then we can perform the sensitivity analysis to understand the which parameter is most sensitive compared to the others. Then we can compare the estimated risk with the decision criteria, and we take the risk treatment action, and we revise the risk assessment with the updated information. Because so if some information is available from the field, we can update the information in terms of the Bayesian probability or the Bayesian updating theory, and then we can go for a revised risk assessment. And this sequence, this kind of application, in this kind of analysis, the application of this probability method plays very important role. The next is that structural control. That structural failure happens if the forces generated to reduce the structural response, that is the stress, strain, or deflection, crossing limit at a certain point, do not function properly. So this generally there is a terms used by Kayamura et al. 2001, that moving average convergence and divergence, MHCD, represents the event of a failure of a control system. The probability of the structural failure in that case is defined as the PF, which is the probability of the Gx less than or equals to 0 on the condition of this moving average convergence and divergence, and the probability of that particular thing. So where the Gx is the performance function, that performance function of anything of that particular structure in hand. So, and the next is the design optimization, where the probabilistic structural design optimization is used, the PSDO, that handle the uncertainties in material properties, geometry, loadings, boundary conditions, and mathematical simulations. So in different types of structure, when we want to optimize the design, then there are different properties. For example, the material properties, where the uncertainty is one of the most important source of this uncertainty. Then the geometry of the structure. Then the loading pattern. Loading pattern means including the dead load, live load, and other the wind load, seismic load. So and the different combination of course. So this kind of loading patterns also is having a most important source of the uncertainty. Boundary conditions. So in fact, in theory, we can define a particular support to be fixed, or hinge support, or the roller support, but in reality, how certain is that? How effectively is that particular support is provided on ground? So there also can be some kind of uncertainty can also come there. And obviously the mathematical simulation, that simulation that we do in the computer, whether that is truly representing the structure that is in reality. So here one example of of a particular overall problem is shown here, where it says to minimize the cost subject to that probability of failure, that is written as PF. The probability of failure is defined as if the GDX is less than 0. So this particular event is less than particular probability that PJ accept. So this is the acceptable probability. So it must be less than that PJ accept, where this D is the design variable vector representing the probability distribution of random variable. The GIDX is the jth limit function. X is the random variable vector representing the uncertain quantities, and PJ accept, as I told, is the acceptable failure probability. So this is an optimization problem. There are this first one, this minimize the cost of the cost function, that D here. So this is the objective function, and there are some constant here under the subject to. These are the constants. So so depending on this, J can vary from 1 to n. So subject to this different constant, you have to minimize this D to get that optimized design for this particular aspect. So here also, when we are defining that probability, and when we are defining giving a limit of this acceptable probability, these are based on this theory of probability or different probability methods. Coming to this transportation engineering, the general source of this uncertainty is generally the vagueness or ambiguity of this traffic condition for a particular road. The risk against safety, this is also one of the most important source of the uncertainty for the transportation engineering, particularly for the road network, and where the mixed variable, which is most of the cases, most of the transportation are having the mixed kind of vehicles. So there, this kind the vagueness of this particular attribute that we are going to estimate from the field condition, the ambiguity, the natural ambiguity that is inherent in the system, these are one of the most important issues that needs to be taken care in the transportation engineering. So here one of the area where the probability can play the role. So again, as similar to the structural analysis, here also we generally want to provide the very low probability, because the associated risk is very high, because these are all in terms of this different toll and others. So we generally want to provide for this transportation engineering, for the transportation system, actually we want to provide very low probability. So particularly the accidents in the air traffic movement, so this is very important, and obviously the probability should be as low as possible. The accident on the highway is also means one of the another very high risk event, so we have to provide the very low probability. So mathematical treatment, if we see for this kind of problems, is that so far as theories are concerned, we can go for the fuzzy set theory. This fuzzy set is a kind of the linguistic representation of the mathematical attribute, of the mathematical condition, mathematical field condition. If we don't have a crisp boundary for a particular event, then we can go for this fuzzy set. Even we can go for the evidence theory, Bayesian probability theory. If we have some kind of belief of the modeler, that belief can be incorporated in these modeling strategies to get the Bayesian probability. Again, as the data comes, so we can update our belief through this Bayesian probability. In this analytical methods, we can go for this fault tree analysis, event tree analysis, multilinear event sequence analysis, and probabilistic risk analysis. So apart from this analysis and analytical theory that is available, we can go to this probabilistic risk analysis if you know that if the information that is available to me is not very certain. Modeling method, the Bayesian belief network, say particular at a particular node. These are actually basically we generally start with some of our data, some of our experience, and once some decision comes to be incorporated, so that decision, that particular information, that particular experience can be incorporated in the model. So the overall thing, the overall information that is available to the modeler is generally get updated, and this thing is generally done in terms of the distribution, probability distribution. Whatever the distribution properties, particularly means the parameter of the distribution that is available to us, those parameters can be updated. These things also will be discussed in details when we are discussing the Bayesian theory. Coming to this water resource engineering, in this again the source of uncertainty is manifold. First of all, the parameter uncertainties. The parameter uncertainties is due to the inability in quantifying the accurate model inputs and parameters. Change in operational condition of the hydraulic structure. So suppose that this change in operational conditions means that can be of many reasons can be there behind this, starting from this climate change, and this available water resource is changed, demand is changing day by day. So these things can lead to the operational condition can change. So that can change. Again, the inherent variability in the model input and the parameters. So that parameters, that particular model that we are using, that model input and parameters can change. So these are the source for the particular that parameter uncertainty. Apart from the parameter uncertainties, there are data uncertainties also there. So in these data uncertainties, the error in measurement is one of the most important and one of the most frequent event that can happen. So sometimes the error in measurement can be of different reasons. One is that the area, that the site where I have to go for this measurement can be inaccessible, and or there are some natural calamities are there where the place becomes inaccessible, or that can be of that there are some willingness of this particular employee who is supposed to go there, take the measurement and come back. So these are the different things, or there can be some fault in the instrument that is being used in the field. So these are the different things where the measurement, the error in the measurement can be there. There are methods how we can rectify these errors if these errors are systematic. Systematic means if there is a systematic bias in this measurement, if we can identify that bias, so that bias can be corrected. But there are some uncertainties is also there, so that error need not be having a particular bias always. So that this is one of the most important cause for the data that we are using. So before we use the data, we have to check for its consistency and its reliability also. Second is the problems in the consistency and the homogeneity of the data. That's what I was just discussing, is that the consistency, once the data is available, first of all we have to see its historical consistency, the historical period that we have using this data, whether that consistency is broken at some point of time. This breaking of this consistency can be due to the replacement of this instrument. Earlier it was located at some location, I may force to relocate my instrument. This is the first thing. Second thing is that due to the advancements of these techniques or the technologies, I can use the different types of instrument after some years, so in the same place. So these things generally shows can be reflected in the consistency of the data. Homogeneity of the data, so whether the data that we are going to use for the analysis is homogeneous or not, that also can be checked through different probabilistic method or different event. So for this one, the deterministic methods are also available. Limitation in the adequate representation of the sample data, as I started with, I just told a few slides back, is that the sample data that we are using must be the proper representation of the population from which the sample is drawn. If for a particular situation, I am forced to take the data that is if that is not possible to take from that is not possible to ensure that the data is from the entire population, then obviously there will be some uncertainty whatever analysis we do with that sample data. Means its parameters will be uncertain, will not be the true parameter for the population. So if there is any limitation of this representation of this actual population in the sample, then that is also one of the important source for this data uncertainty. The third one is the operational uncertainties. This is generally the errors associated with the construction, manufacture, deterioration, maintenance, and the human activities. So particular thing when we go to the site and construct, that may be that uncertainty can be there in construction, in the manufacturing process also, and a manufacturing process, both in the construction and manufacturing process, the uncertainty can be there. Once the structure is built, and the structure here, what I mean is that particularly the hydraulic structure is built, and that can deteriorate over time, particularly say that one distribution pipeline I just fit, and that inside the inner surface of the distribution pipe can deteriorate. So the estimation of the parameter, particularly that if we see that n, that Manning's n, that can be changed for the deterioration. The maintenance and human activities also can lead to the different operational uncertainties for the total system. So if there are different analytical techniques available to measure this uncertainty. The first one is the derived distribution techniques, and second is the probability and quantile estimation. The derived distribution techniques means whatever the data that I am having with, if I can fit that data to a particular distribution, then using that distribution I can give some information of the uncertainty of that is associated in that particular data. In a classical prediction problem, if I say that if I predict some particular value for a particular time series, then that prediction is always associated with some uncertainty. That uncertainty can be quantified in terms of the different probability distribution. So different probability distribution here means that which distribution fits the data well. In terms of that distribution, that predicted value can be associated with that particular distribution. So so that in that way, that is using the distribution technique, that uncertainty which is associated with the predicted values can be measured, can be quantified. Second thing is the probability and quantile estimation. This can be done with the raw data that is available with me, to give what is the spread of this data, what is the range of the data that we can, and we can estimate its different quantiles also, just to know that how it is non-parametrically distributed over the entire support. This can be also very useful for the non-parametric prediction, where I don't have any particular distribution which fits the data well. I can go for some non-parametric way, some quantile estimation in terms of the box plot, and that box plot can also be used to quantify the uncertainty. Again, that also can be applied to this predicted values. The predicted values can be associated with the box plot to give the range of the uncertainty for that particular prediction. There are other approximation techniques also that is available, and these are, the first thing is the first order variance method, probabilistic point estimation method. So this probabilistic point estimation method, where I generally give a particular information. For example, I am estimating the mean of a particular sample, and I am trying to say that its confidence interval of that mean to mean of the population from where the sample is drawn. So this probabilistic point estimation method is one of the approximation technique where I can give some kind of range, some kind of uncertainty band for the particular point estimation. Similarly, that Monte Carlo simulation can be used to, if we have a Monte Carlo simulation is generally used to, if we have a limited data set, I can increase the number of data set, keeping that statistical parameter. The basic idea is to keep the statistical properties intact and increase the number of population, number of samples. Sorry, the number of samples I can increase using the Monte Carlo simulation. The Monte Carlo simulation and the other kinds is that resampling techniques. This is also a kind of simulation, but in a non-parametric way, that jackknife method or the bootstrap method, where that this increasing in the number is generally done without knowing the background, without knowing the distribution of a particular data set. These techniques are generally very useful when the data set is very small, and and the data set is so small that the estimation of any particular distribution can leads to a erroneous result. So without going for its particular without going for the estimation of the probability distribution, I can use this resampling technique to increase the number of sample data. This can be either with or without replacement of the original sample. Reliability analysis for the hydraulic structures. This is also one of the most important aspect, because again we generally assure a very low probability of this particular structures, where the damage or the failure of this kind of structures can lead to a very devastating in nature. So this load resistance interface computation, it can be direct integration method, or it can be the mean value first order or second order moment method. The advanced first order second moment methods can also be used to assess the reliability of a particular hydraulic structure. There is another type is known as the time to failure analysis. This analysis for failure and repair characteristics, and the analysis for the availability and the unavailability of a particular attribute that is in hand in the problem. So in this lecture we have the basic motivation of this lecture was just to introduce you to the different types of situation where the probability methods, different probability tools can play the role, and particularly in the different specializations of the civil engineering. The role of probability studies in civil engineering is to provide the formal basis of this, analyzing the uncertainty and the risk. The different source of uncertainty for the different fields is discussed, and these are the particular these are the area where generally if we apply the different it has been observed that application of this probability methods is very effective and can be very effective for this kind of problems. The risk assessment, reliability analysis, data quality assurance and quality check are common fields where the probability methods are advantageous, and how to do these things will be discussed in the subsequent lectures. We know that why we need to do this risk assessment, why we need to go for this reliability analysis, data quality check, that is also important for its consistency, reliability and all. So these in this particular application, irrespective of any particular specialization, it is generally can be applicable to any specialization. So probability methods are found to be very advantageous. The common probabilistic theories like the Bayes theory, fuzzy set theory, and tools like histogram, measurement of mean, variance, standard deviations are very useful for all different disciplines. However, one thing to be kept in mind is the applicability of anything, any method that you are going to apply generally depends on the type of problem and situation of at which the problem is being addressed. The probability methods are not adequate to solve all the engineering problems. This is also is need to mention here, as I was started with this lecture, that it is not necessary that all the problems that you encounter will be solvable through this probabilistic method. So with this, and there are few references that I cited in this lecture, and with this I want to conclude this particular lecture, and in the next lecture onwards, where we'll go through the module 2 up to module 7 through different techniques. We'll start with the random events, random experiments, and then different commonly used probability distribution theories for the particular application in different problems in civil engineering. We'll see, and we'll go through all these techniques, and we'll also have some problems in these lecture slides also, and some problems also will be available for your own practice. And thank you, and I welcome you for the next lecture on these probability events, the random events. Thank you very much.